Hattori from Kyushu University of Japan. This is the outline of my talk. And first, I introduce the current status of the AM OLED as an introduction. And after that, I'd like to talk about the requirement for TFTs in AM OLED, because some researchers, especially working on low temperature polysilicon, don't believe that amorphous silicon TFT cannot light the OLED. So I want to show you amorphous silicon can light the OLED enough. And after that, I introduce the driving method of AM OLED. This is a subject I'm mainly working on. So after that, I'll show you the AM OLED display using the amorphous silicon TFTs, which we developed with collaboration with Casio Computer Corporation. So I'll show you the panel specifications and driving technologies and OLED technologies. And finally, I'll talk about the possibility of the OTFTs for AM OLED. I focus on mobility, channel type, and structures. And I conclude my talk. Next, please. First, introduction. This shows the current status of the AM OLED. Passive matrix OLED is now mass-produced. You can see it behind the cellular phone. There is a small display behind that. So that is the passive matrix OLED. But that size is restricted to be a very small size, and researchers began to go to the AM OLED, active matrix OLED. So AM OLED has advanced into the phase of the mass production now. Last year, Sony shipped to the market this type of PDA, and it mass-produced 2,000 sets per month. Everyone buy it and sold that, but now they stopped producing because no one buy it anymore. So I had it. So the main reason is price. Price is too high. So in order to surpass the LCD, a major price reduction is necessary. So, but OLED, AM OLED has enough potential to do that because the polarizer film and the color filter and backlight are not required. And these displays using the low temperature polysilicon technology, it's a little bit expensive. So in addition to this, and amorphous silicon TFT and OTFT technologies are strongly expected to reduce the cost of the panel in comparison with the low temperature polysilicon. Next, please. So requirement of the TFT in the AM OLED. So do you know how high mobility is required for the AM OLED? So this is the parameters we calculate the TFT size. And the luminance is of the 400 candela per square meter is needed for the use of TV. So this value is much higher than that for the mobile use. And the efficiency, current luminance efficiency, we assume 10 candela per ampere. This is not so high value. So we can calculate the current density of 4 milliampere per square centimeter, and we are assuming the 20-inch VGF full color panel with 635 micrometer by 212 micrometer pixel area. So we can get the current about 5 microampere, which need for 1 pixel. So under the condition of the TFT like this, and according to these equations, we can get the channel width like this blue line. The horizontal axis is mobility. So we are assuming that this size of the pixel area, the maximum channel width is to be 600 micrometer. That is a red line. So cross point gives us mean mobility required for AMOLED. That mobility is 0.1 square centimeter per volt second. This is required for TV use. So this value is not so high. And also, of course, it depends on the efficiency, but we can say, I can say mobility greater than 1 square centimeter per volt VS is not needed. So there is a chance for OTFT or amorphous silicon to get the marketplace. So the stability of the amorphous silicon TFT, and in terms of the stability, I worry about. So amorphous silicon TFT has instability, a very high instability. So people worry about its affect the image quality or display lifetime. So this is a result showing that instability. So horizontal axis is the input voltage, and in this configuration, that is the gate voltage of the driving TFT here. And vertical axis shows the output current, it's drain current of this transistor. We apply a stress, bias stress to the gate voltage, gate electrodes, and this shows the time of the stress. So after 10,000 seconds, the current level decreases by 40% from the initial value. So since the luminance decreases proportionally as output current decreases, so the luminance also decreases by 40%. So which is a very serious problem. So by the way, the LCD is not affected this effect because it is the voltage-driven device. So this kind of the instability doesn't matter for the LCDs. Next, please. So that kind of instability appear on the display like this as a sticking image. And in terms of the low temperature polysilicon, it has another problem. It's non-uniformity. Low temperature polysilicon has very large fluctuation of the both mobility and voltage, threshold voltage, thus resulting in luminance non-uniformity. And these problems must be solved by a circuit or a driving technique. And I can say that in this stage, which technology I can't say which technology is superior. Anyway, so next please. So I'd like to introduce the driving method of the AM OLED briefly. So this shows the categories of the driving method. There are many driving methods, and this is presented by many companies. So it is mainly it is divided two categories. One is analog, and the other is digital. And area divided and time divided modulation method. That is those are digital driving method, and this method is categorized into the voltage-driven method. And in this method, TFT is used only as switches. So the fluctuation of the mobility and threshold voltage doesn't matter in this driving method. So we can get very uniform and very uniform images on the display, and it can be controlled in a half-tone precisely. But this driving method has a serious problem, that since that OLED is driven by the voltage, constant voltage, the sticking image is very serious. If the OLED characteristics reduce and degrade decrease, the luminance also decreases. So I think that there is no chance to get to be measured for this driving method. So there is no compensation circuit in analog driving, means that there is no it doesn't have a compensation circuit or a driving method. So we must improve the TFT characteristics as high as we can. So, but this has a very low yield. So I think that there is no feasibility. So there is only two choices we have. So that those are current programmed, and the other is a voltage program driving method. Next, please. So current program, those are circuits, pixel circuits for the current voltage, current program method and voltage program method. You can see now 4 transistors for each circuit, and 1 capacitance and 2 capacitance for the voltage program. So difference is programming method. The current program method program the data by a constant current source here. So it compensates for both threshold voltage and mobility variations. And the voltage program method program the data by a constant voltage. And it can compensate for only the threshold voltage. So that point, in this point, the current program has advantage to the over the voltage program. But the current program has a disadvantage, that is the lack of the current source data driver and slow program speed. On the other hand, the program for the voltage program method, the existence LCD data drivers are compatible and the fast programming speed we get. So in this point, the voltage program had advantage. In this stage, I can't say which is very has an advantage, but I believe that current program method will be major because I am researching on this method. Next, please. So next, I'll show you the AM OLED using the amorphous silicon TFTs we developed. This is a picture we developed. and it was presented at IDW 2003. The size is 5.2 centimeter in diagonal, and dot format is 128 by 3 RGB and 160 volt dots. And pixel pitch is around 250 micron in horizontal and vertical, and frame frequency is 60 Hz. And the color arrangement is RGB stripe. So input signal is, we are using 6 bits for each RGB. The color quality is enough high for a red color, but the green and blue is not enough in this stage. It will be improved soon. Anyway, so I emphasize this display has a high contrast ratio. It's more than 100. Real value is much higher than that. We can't measure because our luminance meter is not so good, so we couldn't measure the black image luminance of the black image. So it will be more than 1,000 or something. Next, please. And this display has two advantages on the cost point of view. The one is the amorphous silicon TFT technology, which has lower mobility compensated with low temperature polysilicon, but offers better uniformity and higher productivity. And the other is the polymer LED technology. Compared with the small molecule LED, the development is not advanced, but higher productivity is possible. So, and nowadays, this technology catch up with small molecule LED technology, and lifetime and efficiency is almost the same. So this combination is the strongest I have ever in my knowledge, as long as I know. Next, please. Now, this is a circuit we use in this display. You can see the only 3 transistor TFTs in the pixel circuit. This is the outside of the pixel, and this TFT located on outside of the pixel, so only 3 TFTs were used. So, and during the program time, the current flow is like this, and we can set the gate voltage by constant current source. So the reason we can decrease the number of the TFT is due to swinging the source line voltage. When during the voltage programming time, we lowered this voltage, so current flow, there is no current flow through the OLED during the program time. So we can correctly program the current into these TFTs. This is the time chart, and you can see during the program time the voltage source is lowered like this, and holding time it's higher, it's raised. Okay, next please. This is the pixel size and design. You can see the 3 transistors here, and here, and here. This largest transistor TFT is for the driving of the OLED. And you can see the storage capacitance here, and there is 3 bus line here for the select and the data line, and this is the source line. So pixel circuit is composed of 3 amorphous silicon TFTs and 3 bus line and 1 storage capacitance. And smaller number of the TFT bus line, they help increase the aperture ratio by up to 22% while maintaining luminous accuracy. Next please. So this is a cross-sectional view of the OLED we employed. So we are using inkjet printing technology. We need a bank to define a pixel emitting area. And the new point is employing interlayer. This interlayer is can improve the charge balance. So we can get higher efficiency and higher and longer lifetime. And yes, next please. And this graphic shows grayscale uniformity. We measured the uniformity at the two levels, two half levels. So deviation is less than 5%, very uniform. And this is long range, distance range. So in the short range, we can get better uniformity. Next, please. So finally, I'd like to discuss the possibility of the AM OLED with OTFTs. So this is a comparison between the amorphous silicon TFT and OTFT. So mobility of the amorphous silicon is in a range of from 0.1 to the 1. But that of the mobility of the OTFT is around here. So the mobility is almost the same. I can say that. And channel type. For the channel type, the amorphous has only an N-type. So P-type amorphous silicon exists, but that mobility is very low, lower 2 orders of magnitude by magnitude. So I mean 10 to the minus 3 or something. And oppositely, OTFT has only a P-type, and it also has an N-type, but N-type is very unstable and small. It has small mobilities, and so we can. I think the only P-type is available, and the structure they have a difference. The amorphous silicon TFT usually has a top contact, I mean an embossed staggered type structure. And OTFT has both structures, but considering the resolution of pattern, so I think the only bottom contact structure is available. So first we want consider and discuss OTFT mobility and driving for the driving TFT here. So this calculation is the same I mentioned before. So and so that I can include that only 0.1 volt square centimeter per volt second is required for driving AM OLED, even in case of the OTFT. Next. Next channel type. So this channel type difference gives us a big advantage to the OTFT. So amorphous silicon TFT has only an N-type channel. So the pixel circuit configuration is like this. So the OLED must be connected to the source of the driving TFT. So this configuration is called the source power configuration. So if the change voltage across the OLED is changed, the gate voltage also changed because this is the source and gate. So it means if the OLED characteristics change, we can luminance also change. It results in a sticking image. On the other hand, OTFT has a constant current configuration. The source is the side of the source line. So the change of the characteristic of OLED doesn't matter. So the gate voltage can keep constant, and the same current is followed. So the OTFTs provide an ideal configuration to suppress the sticking image issues. Next, please. So lastly, I talk about the TFT device structure. So usually amorphous silicon has this type of structure. And bottom contact structure is also possible, but everyone use this structure because of the overlap region. Overlap region is not good for parasitic capacitance, but good for contact resistance. So overlap region helps to decrease constant resistance because this area getting larger. On the but OTFT has only bottom contact is available because patterning on the OLED is not now available. So in case of the OTFT, there is no proper process to define a source and drain electrode in the top of contact. So that's this kind of this proper process is strongly required. Next, please. In conclusion, so AMOLED is in a phase of mass production, and the most important issue to obtain a larger market share is the cost reduction. The AMOLED we have developed employs the unique combination of amorphous silicon TFT and the PLED technology to achieve the greatest cost reduction. The 3 TFT pixel circuit can successfully achieve the very uniform halftone images and high aperture ratio, and mobility is not a key issue for OTFT technology since AMOLED requires mobility only 0.1 square centimeter per volt second. Thank you very much.